Hello, everybody. You're very welcome to this Going Public lecture. It is the number 25 by now in this series. This lecture of tonight is in the Craftsmanship engagement and will be introduced by one of the tutors of our faculty, which is Laurens Luyten. So maybe Laurens, you can introduce the speaker of tonight. Very welcome.
Okay, it will be my pleasure to introduce him. Also, my welcome to everybody. I would like to start this introduction by presenting you a little sketch. Imagine that you are a designer and you receive a brief for a new design project. The context is known and the program is set. It needs space, form, and materials now. It needs a design. Instead of sitting at your desk and developing ideas for this project, you walk in the hallway and open a door. You enter a room, a very large room actually, the size of a factory hall. It is full of design models, not 10 or 100 or 1,000, but millions. All these models you see in front of you represent possible design solutions that follow the brief and context of your design project. You take two models in your hand and you see that they are only slightly different, but they are different. You overlook the array of models, and the further you look, the more different the models become. Now your work starts to search for a model that you find best suited for the project. How would you go about finding this so-called best model? And when you find one, how would you know there is not even a more suited design solution that was not represented in this hall? Maybe this sounds like an utopian or even dystopian design situation. But with current computational power, the generation of all these design possibilities and various selection processes are a reality that can be found in the academic but also in the professional world. Lennert Loos is at the front line of this generative design in both worlds, and it's my pleasure to introduce him to you. He studied at the VUB in Brussels and received a Master of Science in Architectural Engineering in 2015. As a student, he was co-founder of the student organization Brutecture, and he was also at the root of the Architectnics lecture series in 2015, which investigated the relationship between engineering and architecture. In 2019, he obtained at the same university a PhD in architectural engineering under the supervision of Lars de Laat and Kenny Verbeek. The title of this thesis is Structural Design by Means of Data Visualization. In this work on generative design, he investigates how to make structural design decisions through visualizations that compare various design possibilities. After finishing his PhD, he started to work at the structural engineering office Ney and Partners, where he currently still works. Here he is involved in the refurbishment project and bridge designs, where he engages in structural calculations, form finding, complex digital geometries, and developing computational strategies. And so over the years, he developed expertise in structural analysis and optimization, complex structural geometries and systems, conceptualizations of structures, bridge and shell design, form finding, generative and computational design, and digital design environments. He is specifically interested in digital design processes and methods, for example, on how to gain insight in digital models and how to compare structural design alternatives, but also how to include the important non-numeric parameters in the design process and how to predict their impact on the design outcome. As you can hear, there is a lot to tell about Lennert Loos. I only talked with him on a few occasions, but every time I saw a man with passion for this field and with an interesting vision. So I think it's time now to let him introduce you into his view on this world of designing structure and architecture. Lennert, you have the floor.
Okay, first of all, thank you, Laurens, for the nice introduction, and you quite summarized already what I'm going to tell, so we can end up the lecture about here. Given my profile and my expertise, I am expected to talk about digital prototyping and digital design processes, but when I heard about the theme of prototyping, I could not resist to also include this project. It's a project that I'm still very proud of. It was built back in 2017, and I will talk a bit about that. So it was initiated, the entire project, by students at the Vrije Universiteit Brussel, the VUB, where every year a architecture week is organized, and that year crazy students had the idea to design and build a inflatable structure in which all the events that take place in such an architecture week could be hosted. So film screen, playing, workshop, lectures, and many more. And I wanted to include this project in the lecture because I think it would never have been possible to realize this project without the practice of prototyping. And so this brings me to the question, what is prototyping? Is it like this image suggests, is it getting strangled by complexity or the size or scale of the project? Is it learning? Is it making tests? And I think it is indeed a bit of all of that. And the two people that you see on the picture here are the main forces behind the project. It's Bastien Damsin and Thibaut Brands, and the latter one is currently also a colleague of mine. So we had no idea how to start with such a project. So we read some literature about it, and we started looking up the Platonic solids, and we tried to look for a shape that allowed us to approximate a bit a spherical shape, because in the end we need to inflate the entire structure. And so by unfolding the entire geometry, we created a kind of cutting pattern, as you see on the right, and then the main job starts. So you buy sheets of foil, you have some patterns that you need to cut out, then you cut all these patterns and you tape them together. And so we used tape in order to seam all these different patches of foil, but we also explored other ways of manufacturing. For instance, welding different sheets of foil together with the help of ironing and burning these edges together, or melting these edges. And so that's what you see here. So in the end here, we have a lot of flat material connected to each other, but still flat on the ground. And then the first test was to actually inflate the entire structure. And that was the first time that we were able to actually feel and see how the structure reacted on being inflated. We could see how much force it could take, how our duct tape was actually working. And you see that we use very high-tech equipment like the fan of the secretary's office. But in fact, this was the first time that we actually gained knowledge about this kind of structure. And I like this picture a lot because it shows the different scales and it shows the process that we have been through, starting from very small paper models. And in the background, you see not a flat paper model, but an inflated more round structure, partly inflated. But obviously, in the end, we wanted to organize a whole range of events inside this entire structure. So I think it was a good idea by the students to already organize a screen playing inside our first and last prototype that we made, because we had no idea how people would react while being inside and being surrounded by plastic. There was only one entrance. That was also our exit, so we were not really sure how people would react in terms of how at ease were they when inside. Was it getting too hot in there because you are working with beamers and a lot of equipment, electricity? Was it maybe getting too moisty? But in the end, everything went very well. And I think we were all very pleased with the result. And we were convinced that it is indeed possible from an architectural point of view to host all these events in such an inflatable structure. And obviously a whole range of inflatable structures have been built already, but not with the very limited budget that we were working on. I mean, we in the end, our final structure cost about, I think, 1,800 euros, which is not a lot, or just 1,000 euros, I'm not sure. But it was really a very limited budget, a limited amount of time that we had available. And obviously we were working with students, so we were non-equipped. We had not material and equipment to build it. So it was all very low crafty, let's say. And we were also ourselves not really experts in fabricating such structures. And then my biggest concern was obviously the wind loads, as it is a giant structure and the idea was to inflate it outside. So as fast as the first prototype was made, I gave the advice to, as soon as possible, get it outside and feel and see how the structure is reacting on large wind forces. And by having this model, we learned a lot. We learned that duct tape is quite good in making airtight seams between these patches. We learned also that the foil that we used was not so durable. Tears would appear very, very quickly. You see also that some air gaps might be present at the place where all these patches corner together. And also you see that the final shape, even when inflated, is kind of spiky, and that's something that we did not like at all. It's not a very pleasant aesthetics of such a structure. So in the end, we learned a lot by doing this very low-tech prototyping. So we wanted, first of all, a more round shape. And so we looked into literature about how can we obtain a more round geometry. And obviously you can do that by decreasing the size of all these patches of which your entire structure is made. But that would also lead to an increase in the length of duct tape that we would need. And the duct tape was in fact the most expensive part of the structure. It was 50 cents per meter. But if you do that for a large air bubble with a diameter of 15 meters, then it counts up quite quickly. So that was not really a good option. So we shifted from the idea where at first we were thinking about dimension maps and making relations, the dimension maps of Buckminster Fuller, and relating that to the final structure. But we shifted from that idea towards, let's say, a beach ball or the more regular Mercator map. And so with all the knowledge that we had about what is the time needed to cut, what is the time needed to patch everything together and to apply tape, we optimized a bit for minimal tape lengths. And this is what came out. And then we had equal parts that could be cut out multiple times. So we laid out a pattern on the floor, and then we align our sheet of foil on the ground and we cut it out. And as you can see, this is a very, very quick process. Jokes are not working in Zoom, right? So then we had all these patches of foil, and then the most difficult part of the job started. We needed to tape them all together. But where we started initially with these icosahedra shape, this dimension map, they are all flat, but you can already assemble quite a lot and everything remains flat. While now with this beach ball shapes, with every part of the seam that you tape, your flat structure is becoming more curved, because in the end we are working with a spherical object. And so that's quite difficult, and we taped not only the outside or the inside, we wanted to tape both the inside and outside in order to reduce the air losses in the large balloon. And so we started at the outside, and once we had the outside seams taped together, we blew it up a bit and people could go inside and also tape the inside of the seams. And you see that we shifted from materials, so not anymore this very cheap foil, which was prone to little tears. And we shifted towards a reinforced construction foil that you often see on formwork. And this has the advantage that when a tear is appearing in your foil, that it is just that it remains inside the little squares that you see, so the reinforcements, and so the tears are not getting any bigger. So that was a great advantage, and also from an architectural point of view, there was a kind of blurriness in the interaction inside outside, and I'm quite pleased with that final result, and especially from the outside to the inside, you see that something is going on, but it's not totally clear what's going on. And I think that's a nice architectural, but let's say, feature of the material that we used. And then this is the promotional video that I made for the Architecture Week then back in 2017. And it is displaying the first time that our very large air bubble was inflated, and we did it in the sports hall at the university. It was the first time that we actually knew that it was possible, that the shape that we wanted was also achieved. But it also learned us about the erection phases. How are we able to control the way this entire structure would be inflated? Are we able to rotate it? Are we able to keep certain points down or up? So we learned a lot in doing this entire process. And so you saw in the video also people pushing against the air balloon. That's to have some kind of insight in the forces. So I did some minor calculations on the internal pressure and what pressure we would need in order to resist external forces, which is in this case only wind. And based on that, we had some measures about the stresses that would occur in the foil, but the uncertainties are so large in this structure. The students were working with tape. We had no guarantee. It was not guaranteed that all our seams were fully airtight. We were not really sure how well the bond was between the foil and the tape at every place, because the difficulty of having this curvature that you need to tape. So there were a huge amount of uncertainties, and in the end, you can do as many calculations as you want, but it remains a bit like cowboy engineering, in my opinion. So it was really good that we had done all these tests and that we started with small models, and that we really felt how the forces on the structure were acting. And so initially the idea of the students was to inflate this giant balloon on top of the roof of the engineering department at the VUB. So you see that it is held down by a network of cables. And so how this structure actually works is that you inflate a whole bunch of air inside the structure, which is causing an overpressure inside, which wants to go outside, and that overpressure is larger than the atmospheric pressure, and that brings your balloon in a stable shape. But at this point where we inflated the large air balloon on top of the roof, I was very happy that the students felt that it was not a good idea to inflate it on top of the roof, because of the large wind forces, because of the configuration of the building. So we had really large forces over there. And in fact, the structure could handle these wind forces on its own, but we had no guarantee that it would just not be blown away by the wind. So in itself, the structure was quite rigid, but we needed to anchor it to the ground. And so that's why you see these cables. But having a concrete slab, a floor, we were not able to anchor the structure quite well to the ground. So I was very happy that we decided to just put it on the ground. It would also not have been very nice to read in the newspaper an article with a title like 30 people dragged off the roof by wind, while sitting in a large air balloon. So I was very lucky to be on the ground again. We inflated it. We used large vessels of water to ensure our anchorage system, and we used 1.5 meter steel pins in the ground to keep everything at its place. And I think this picture shows very well the size of the balloon. It's a kind of surreal size, and in the end, we were all very happy with the result. And finally, the Architecture Week took place, and the whole range of events were organized inside. So this is a picture from the inside. And so you can see what atmosphere was inside. It was quite hot as well. It's like a greenhouse. So even when you are blowing in fresh air at a constant, very high rate, even then it was quite warm. You can see some wrinkling in our foils, but it's only at the edges. So having only this limited amount of wrinkling means that our structure was fully tensioned, and so that we had not made too much errors on patching these, of assembling these patches together. It's always a bit tricky to make pictures inside a sphere because of your camera angle, so it's difficult to show how large it in fact was inside. It had a diameter something like 13 to 15 meters as a whole. But a film screening was organized inside, and I think this picture really shows the tremendous size that we were able to achieve. And in the end, we did not ask permission to all authorities to actually build this structure, and I think that's a great thing that we did not do, because in the end, you won't build such a crazy, surreal thing if you are really asking authorities for permission to do all these things. So we had parties and receptions inside. We also experimented a bit with projections on the surface of this balloon. And this is the picture where I started from, and this is a picture that resonates very well, I think, what this whole project was about. You see people inside and outside. You see the blurriness as a boundary between inside and outside. You see a rather nice geometry. It was rather slick. It was executed in a very slick way, I think. And it also shows the relationship and the scale in perspective of the other buildings. So a great thanks to all the people who were part of this project. So I think this project really shows what prototyping is about. It is what I told is a very traditional way of defining prototyping, I think. So it is according to the scheme where you make a certain design, you build it, and you build it in a sloppy way, or you build it in a sound way. It doesn't matter a lot, but you test it and you make assessments based on the build that you made, and then some issues will appear. You fix it and you go back to the drawing table, and this iterative loop is how you will finally end up with a sound design. But obviously, for buildings, bridges, real structures, we are not going to do this whole cycle of making pre-builds and tests of the entire structure. So what we do is we design, we analyze it with the help of models, then we test it, and finally we build it. And so I'm expected to talk about digital prototyping, which is in fact more or less the same, where you also design something digitally on your computer, you analyze it with the help of digital tools. So that could be structural analysis or analysis of HVAC, but also what are the aesthetics, what is architecture, how well is it in perspective of its context. And then you test, you make assessments, you try to gain insight in all the design parameters that are part of the project. And finally, while having done all the assessments, you are done with the design and you build your entire structure. And so if you think of modeling and structural modeling. So from a structural design point of view, you immediately think about the models that Gaudi and Fraiotto made with the help of hanging change and soap models, not only to understand what the structural behavior or the structural form finding was about, but also to see how the final structure would look like. And so they were gaining, just like the story that I told about the large air balloon, you are gaining insight, you are gaining an understanding based on making models and tests. And based on that, you will proceed in the design. But obviously now we have translated nowadays the laws of nature into algorithms. And so we can do it digitally at our desk with the help of computers. But that brings to the front the question, in what way are we actually gaining insight with the help of digital tools? How well are digital tools facilitating design? And in design, it is important that you make comparisons, that you are aware of certain design choices, that you are aware of the impact of that. And so while doing research at the university, I investigated parts of this digital design process. And I would like to show a small example to show you the, let's say, the pitfalls that might appear while designing digitally. And I would like to refer to a project of NEAM Partners in Antwerp, the Osterried house, where the design of NEAM Partners involved the design and construction of 2 glass and steel grid shells on top of an existing 2 existing courtyards. And so this is what the final result looked like. But from a digital design perspective, we have a lot of tools available. We can do form finding, we can make structural calculations on the computer, we have parametric modeling tools and optimization. So we have endless possibilities to generate a whole range of design solutions. And that's also what Lauren said in the introduction. So there is no issue anymore to explore your creativity and to come up with a million different design alternatives. So we can make minor or major changes, and we can come up with a whole bunch of different design solutions. And from an aesthetical point of view, an architectural point of view, you can have a certain preference about which design alternative you think might be the best solution. But from a structural engineering point of view, you want to get informed about the structural behavior, about what is the total mass of the structure, how sustainable is our structure. You have questions to solve about how will it be constructed, what are the reaction forces on the existing courtyard walls. And so these are things that needs to be, just like in prototyping, that needs to be assessed. By making comparisons of a whole bunch of design alternatives, you actually get informed about a whole series of these questions. So you get informed about what is the influence of a certain design parameter and what is the impact on a whole series of assessment parameters. So how do we get from a series of design alternatives towards our final choice? And so the question that I will ask today, let's assume that we have parametric models and that we can generate 1 million different design solutions. How, as a structural designer, are we able to actually make informed decisions, and how are we able to understand what these differences between all these different design alternatives that we generate, how are we able to understand what these differences actually are? But obviously, as we are working with parametric models, we are in a digital environment, we set up a script that makes these geometries for us based on a script that we made ourselves. So as we are working digitally, we can run optimization algorithms. And so this graph shows schematically a objective function where, for instance, the total mass of a whole range of different design solutions are put into a single graph. And so if we would like to have the lowest mass, well, then we just search the optimum, which is the dot at the very bottom of the graph. But that brings us to the question, are we going to let the computer decide which design alternative is the best solution? Well, what the computer gives you as a solution is indeed the best solution for the boundary conditions that you say to the algorithm to search for. But obviously, as I said earlier, there are a whole range of assessment parameters which are non-numeric, which can hardly be integrated in algorithms, like architectural preferences, certain requirements made by the client, just also knowledge that you know from previous work that you have done, certain expertise that you have. It's hard to translate these in a pure optimization algorithm. So why would we just optimize for mass if that is the final solution? And secondly, engineers or designers, whatever, architects, they do not like to just get a single design alternative as the proposed as the optimum from an algorithm, and then what are they supposed to just work with what they got from the computer? That's just not how designers work. But all right, we just looked at the total mass of the structure. Maybe including other parameters might be a good solution. And so what you typically get then is into the field of multi-optimization, multi-objective optimization. And this graph shows for a series of cantilever structures. So all the dots in these graphs are different design alternatives. And on the vertical axis, you see the deflection, and on the horizontal axis, you see the mass. And so this is typically what is called a Pareto Fold, where you see, let's show my pointer, where you see all these different design alternatives, and all these black lines are part of the so-called Pareto Fold. And so up here at the left upper corner, we have design alternatives that have a very large deflection, but a very low mass. If we go to the right bottom, we have a very large mass of the structure, but a very low deflection. So what is then in the end the optimum solution? The optimal solution is mostly found in this area, but still we have a lot of different design solutions to choose from. And what then to choose from? So in the end, even with multi-objective optimization, we end up with a whole series of design alternatives, and it is still up to the designer to make the balance, to make a trade-off, not only based on numerical parameters, but also based on non-numerical parameters, and to choose for what is the best solution to him or her or the entire design team. So it's not a very straightforward solution to say what the optimal design is, and it is especially not easy to just refer to optimization algorithms. Okay, so structural designers want to understand differences in the behavior and in the forces that are appearing in structures, and based on this structural behavior, they would like to gain insight in the differences in design decisions. For instance, what if this entire shell is supported only at the corners? What if we also have support at the middle? What is the influence of the actual grid pattern? What is the influence of the entire shape? And the question is, it's quite difficult for structural designers to design structurally. And that is mainly due to the software they are using. So what you are seeing on the screen right now is typically what structural designers are working with. These are the finite element modeling softwares where you translate a certain architectural model into a structural calculation model. You put some loads on it and you will get the internal forces, deflections, dynamics. You get a lot of information about how the structure is actually behaving. And so, for instance, here in orange, you can see the tension forces. So you immediately recognize we have large tension forces here in these edge beam around the middle of each edge beam. You can also see the tension forces here near the corners, and the rest are then elements that are in compression. But we were not discussing just a single design alternative. These softwares are quite good at showing what the structural behavior of a single design alternative is, but we were talking about a whole series of different design alternatives that we would like to investigate. So we have also a lot of data that you can fetch from these finite element softwares. So you can process the data manually. But we were not just discussing a single design alternative. So let's go to a other design alternative. You see a different layout of the grid. Okay, so you try to understand, we have indeed the same tension forces over here. We have another pattern. Okay, the compression forces are in these elements rather large compared to the previous one. And we have also tension in these ribs at the diagonals. Okay, so we try to memorize and then we go over to a third design alternative. Okay, other boundary conditions, maybe other grid typology. And so we try to understand what's going on. But by now showing 3 different design alternatives and having arrived at the third design alternative, you all already forgot what the first design alternative was about. And that is actually the main issue with the software structural designers are often using to design. But obviously we have all the data at hand. So what you see is that engineers will fetch all the data and then manually post-process all this data in order to make some informed decisions. And this flipping of screens that I'm showing is really this is what engineers are doing most of the day while actually designing. So these softwares are made to code check and to understand single design alternatives, but not so much for comparing. And that's why comparing is so crucial for gaining insight and for the process of designing. So that brings me to the major question of this lecture. How can we compare structurally the behavior of a whole range of design alternatives that can be created very easily with the tools that we have at hand right now? And obviously, as we have all the data, we could use statistics to gain insight in the data that we are working with. So we have a data set over here, but it says nothing as such about the data itself. And that's what this next slide shows. So these are 4 data sets that have identical statistical analysis measures. However, as a human, you immediately see that we are dealing with different data sets, and you can immediately relate the properties of single data points to each other, while they are all having the same statistical data measures. So it's good to work with data, it's better to visualize the data. And indeed, we see in a whole range of other disciplines that, such as economics or social sciences, that data visualization is not only used, as in this case, for presenting in an understandable way complex data sets, but that it is also used as a way to explore your data and to understand what's going on in your data. And so the main question I wanted to answer in my research is, can data visualization help? Can it be of any help to actually gain insight in the complexity of data sets that are embedded within a whole range of structural models or alternatives? And so to investigate that, I developed a few case studies, of which I will present 3 today. And so have a look at these 26 different alternatives for bowstring bridges. And so you can see that the arch geometry, the form of the arch, is more steep at the top row, and that it's getting more round towards the bottom. You can see single cable configurations, triangulated, intersecting, and then some kind of hyper configuration of the cables in the last column. These geometries are all form found, which means that in some way they are all very efficient, but as they differ in geometry, they will also differ in structural behavior and in performance. And so what you see in structural design offices, and I think it's good that that is done, that you try to compare different design alternatives, you try to look at the maximum forces that appear in your structure under several load cases, also what the displacements are. And based on that, you make informed design decisions. And what I like about this table is the last column, which gives an indication about the aesthetical appreciation that the designers had at that time in the design process. So it really shows that designing is not only about numbers, but that it is about trying to make the trade-off between numbers, aesthetics, architecture, and a whole lot of numeric and non-numeric objectives. But in the end, this table is quite unreadable. We are dealing with numbers. It takes a long time to read it. So what I tried to do with the data set of 26 different design alternatives that I showed earlier is to translate such a table into a visual table. And it's not very high tech, obviously, to do this, but it gives a whole new perspective on working with data, as you can see the values visually, and people are trained to immediately see differences in such bar charts. And especially when you are able to relate your visual representations back to the geometries you are dealing with, you are able to make, so you are able to gain certain insights based on design decisions. So for instance, what is the influence of using this very sexy cable configuration? Well, if we look at the first three columns, which represent the actual forces in the arch, deck, and the cable, there you can see for the arch and the deck that the internal forces are not very different from the other design alternatives. For the cables, the internal forces are obviously a bit larger, so it doubles the magnitude. But what you see especially is that the bending moments in the arch and deck, and also the displacements in the arch and deck, are tremendously more are very big compared to the other design alternatives. And so that plotting this table allows you to quickly understand certain design decisions in the perspective of the other design alternatives that you came up with. Let's have a look at other cable configurations. So we keep the same form of the arch. What if we go from a single cable configuration to a triangulation and towards more and more intersecting cable configurations? Then you can see a slight reduction of the internal forces in the arch and deck. But especially you can see that the bending moments in the arch are decreasing a lot. And so we have all the data at hand, so why not just visualizing it, linking it back to the geometry, and getting informed about what we are dealing with. And some other things could be visualized in order to gain further insight. But this table is in fact based on the maximum force in the arch, deck, and cable, the maximum bending moment and the deck. But that's just one local value in the structure, and it's not always a good idea to summarize your entire structure just based by maximum values. So what I tried to do in this graph is, can we assemble all the available data into a single graph and represent the structural behavior of all different design alternatives? And that's what you see in this graph. So all the different design alternatives are plotted in here, with at the top part the tension forces in the deck, and at the bottom the compression forces in the arch. And so you see in blue the design alternative that is showed on the left, and you can clearly see the progression made while going from one side of the bridge towards the other side. And so you can see that our internal forces are rather large near the ends in the arch, and that it is decreasing, so going more towards zero, that it is decreasing in the middle of our bridge. And it allows you to not only understand the visual, the structural behavior, because in some way this is very similar to the force diagrams engineers are used to work with, but it allows you to put it into the perspective of all these gray other behaviors of the other design alternatives. And so again, if you are able to relate your structural design alternatives with your graphs, then you are able to gain further inside. So we are making progression from a more steep arch towards a more round arch. And then you see that the internal forces are decreasing while getting towards a more round arch. And so we need some digital interfaces that allows you to work more easily with data and to more easily do data operations in order to gain an understanding of all the data that is embedded in our digital models, I think. But in the end, bridges are quite easy in the way that the representation can be done quite easily. It is a one-dimensional structure. You go from one side to the other, from -1 to +1, so to say. So let's increase complexity and go back to our grid shell model, which is in fact a two-dimensional structure. We have a Y and an X axis. So in order to investigate this, I created 16 different design alternatives with different grid layouts, different support conditions, and also different overall shapes. So the C stands for compression only. These were form-found design alternatives, and then we have a free-form design alternative, or an alternative for the overall shape, which is just an architectural choice that has been made, but it is not structurally informed. So again, I wanted to include as much data as we have. So if we take a look at the structural model, you see that every element has a certain internal force, and I wanted to include every single element. And that's what you see in this graph. So you see each column, there are 16 columns in total, each column representing a single design alternative. And the names are then plotted underneath. And on the vertical axis, you see the actual force of the elements. And so the plot you see is a histogram. So that means that if we have a very large, a very wide rectangle like this one over here, that means that a whole range, a lot of elements within this structure are having internal forces near zero, while this is a very short subdomain of the entire axis, and we have just a very few elements with very high internal forces. And so this graph, it is a bit tricky to read at first. You need to get handy reading it. But in the end, it allows you to gain an understanding in the distribution of all forces that occur in your grid shell. And especially when you are able to make interactions between, when you are able to interact with your graph. And for instance, here you see in black all the free-form design alternatives, and in gray the form-found design alternatives. You can really see that for the free-form design alternatives in black, the distribution is very widely spread, while for the compression-only ones, you see that most of the elements are in compression and have rather low internal compression forces. You could do the same for the bending moments. It's, I think, not so interesting to go deeply into the case right now. But you can see, for instance, the first 8 design alternatives are the compression-only structures. You can see that the bending moments are rather low, so they are near zero, and that the largest distribution is focused around zero. While if we go to the last 8 design alternatives, which are free-form, we have a whole range of different different bending moments among the elements in the structure. But as we have all the data in our structural models, we have a set of design alternatives. We could, for instance, go much further and also investigate what the sensitivity of certain load cases or combinations are. For instance, we plot all the elements of a certain structure. So what's the internal force under snow and then under wind, and we can see what the progression or the transition of internal forces in all these elements is. What is important, and I think the graphs that I showed for the grid shell are lacking that a bit, is the interaction between our structural geometry, the way how we design. We design digitally, we design with the help of Grasshopper, Rhino, Revit, I don't know, but you look at the structure you are designing. And beside that, you want to get informed about the forces. And graphic statics is often proposed as a very, it is suggested as a very educational tool. And the reason for this is that we have at the left, for each case, the form diagram, which is actually the geometrical representation of your structure. And at the right, we have the force diagram. But how to read it, we apply some forces on the structure that are these blue lines. So these are these 4 forces that you see over here. And then you see that all these elements have the same orientation as the elements in the structure. So that means that this element is one-on-one related to this element. And so you can, and this top element is one-on-one related to this one. And so this force diagram is a polygon of which the length of each line represents the magnitude of the force. And so you have a one-on-one relationship between your actual geometry and your force. And that was missing in the graphs that I showed you earlier. So I think it is important, and graphic statics does that very well, that we should have a certain link between the geometry we are working with and the data we would like to investigate further, in this case, forces. So what, for instance, if we go back to the grid shell design alternatives, what if we would like to see where these 15% largest compression forces are located in the structure? So that are this selection in black. Well, when you have an interactive environment, an interactive design environment where you can make these selections rather easily, you can visualize where these elements are located in your different design alternatives. And by doing that, you are able to see certain similarities between different design alternatives. So for instance, in this case, you see that the largest forces are in the diagonals. Here, where we have another support conditions, but still we have the largest forces according to this diagonal pattern. We have other design alternatives where it appears in a more hashtag shape. And so it is really important that we are able to work with the data, not only by plotting graphs, but just that we are able to handling the data very easily. And so we can create graphs that we can make selections like I showed you here, and then refer back to our structural geometries. This is another graph on the vertical axis, the actual forces, so the normal forces in our grid elements, and on the horizontal axis, the bending moments. By making selections, we can see which element is located where in the structure. And so the normal force and the bending moment allows you to give and to have a certain understanding about the characteristics that certain elements need to have in terms of cross sections. And so, for instance, here where we see the red design alternative, it is very dense. We can cluster very dense groups, which means that the cross section of these elements might be rather similar, or might be we might need less cross sections, less different cross sections for the red design alternative, while in the blue design alternative you see that it is scattered around all over the place, that it is hard to have very condensed groups of data points. So that would mean that if we design optimally, that we would need a larger range of different cross sections, which is all information that is important for the structural designer in order to proceed in the design process and to gain insight in what in the questions that are asked, and to come up with suitable solutions. Also, another graph that shows a cross-section optimization algorithm. And so you see the transition that is made before doing it and after doing it. So you see the actual forces in these structures of each element, and you see the transition of all the elements going from before towards the internal forces after the cross-section optimization. And so you can see in black that most of these elements are not changing very much in their internal forces, but however you see that these blue elements are making a giant transition. And then it is important to know where these elements are located, and so you can refer back to the geometries and see where they are appearing in your structural models. And then the last case study that I would like to present, but I think it's really a relevant case study because it was in collaboration with Bollinger Grohmann, and so it was inspired by problems that are present in the structural design practices. So it is not just an academic exercise, it is really something engineers are dealing with today. And so it consists of the design problem. Well, every problem can be solved. So the design question was, where do we put cables in the facade in order to come up with a suitable solution? And so the structural system of the facade was like this, where we have vertical columns in the facade, but at ground level you see that we have only half of the amount of columns present in the structure. And so the idea was to include cables in order to keep the bending in this transfer beam rather limited and to keep the entire structure slender. And obviously we could opt for performing optimization algorithms and for mathematically looking what the best solution was, but that would give very predictable results. And from an architectural point of view, the engineers and architects chose to opt for a solution where the cables were in a homogeneous way randomized across the facade. So something you are seeing right now in blue. Okay, what are the tools of the engineers? So I showed you the process, cycling through windows, handling and post-processing the data in Excel, which is very time-consuming. And also the representations we have for understanding the structural behavior are quite difficult to read, and also they haven't changed for the last 50 years. So I think working with data can really help to gain insight in structures more quickly. But even if we make it clearer, so let's make a selection of the facade only and just display the beams and columns and cables that are present in the structure, even these different design alternatives with different cable configurations, only comparing these two design alternatives becomes very difficult. It's very hard to see what the differences of the cable configurations are and what the effects, what the impact of certain differences in cable configurations have as an impact on the total performance, the structural performance of the structure. So the first thing to do then is to manage your data wisely. And then when your structural model and your data model is structured quite properly, you can unfold your entire facade and you can make a representation of what your facade looks like. So you can easily see where your cables are located. You can apply certain line thicknesses and colors inside your facade in order to see what is the local effect of applying a cable in a specific position. But then you also see that I put some line graphs underneath, which are giving additional information locally about the configuration of the cables. And so what you see is, for instance, in the first graph, what the reaction forces at the ground level are for different design alternatives. So you see not just a single design alternative is plotted in these line graphs, but that a whole range of different design alternatives are plotted. So it allows you to understand a certain design alternative that you are interested in and to investigate it in the perspective, in the context of the other design alternatives. And so you can see that the forces in the ground floor columns is the influence of cable configuration is rather limited. There are some minor, the range is rather limited. But then if we look at the deformation energy in beams, so how much deformations are taking place in the horizontal elements for each facade part, then you can see that there are very large, that there are structural design alternatives that show with very hysterical behavior because of their cable configuration. And so based on this, you have a lot of information at hand that you can actually use to make informed design decisions, so that you can use to prototype, to understand what certain design decisions have as an impact on your structural behavior and the performance of your structures. And so you can do this for not one single structure. You can do that for an optimized one, which was not a good solution in terms of architecture then. We also used evolutionary optimization algorithms in order to get a certain randomized pattern. And we wanted to look what the influence of certain cable configurations was. And so finally, we did not end up doing everything digitally. We just plotted it on paper, these representations. But by doing that, we were able to characterize certain parts of the facade that were working structurally very well and parts of the structure that were working rather badly. And based on having all this patchwork of well-performing and bad-performing cable configurations, we were able in the end to reassemble a facade geometry with a cable configuration that was, first of all, quite well performing in structural terms, but secondly, also from an architectural point of view, it was well performing, as it was indeed randomized. So what I would like to summarize what I have been talking about thus far. We have a lot of data available in our digital models. Is it just geometrical data? I mean, if you make a grasshopper model or a Revit model, we have a lot of information about angles, about the sizes of plates and walls, what is the volumes of columns and elements that you are using. There is a lot of data there. If we calculate these structures, we also have a lot of structural data. So why not use it? The question, can we use data visualizations? Yes. So don't work with data in a blind way, not just use the data, but use data visualizations. But also don't just use data visualizations. You still need to refer back to your three-dimensional geometries. And so that's what this image is showing. So not just the data, not just your structural geometries, but there must be a certain interaction. And to investigate the interaction, I have been developing a proof of concept tool of which one part was a Grasshopper plugin, and it allowed you to define graphs based on data within Grasshopper, structural data from finite element models, and to plot it directly in an interactive dashboard in the web browser. And so you can highlight certain elements in order to see where these elements are located inside the structure. But the entire thing was fully interactive. And so, for instance, in Grasshopper, if you change a certain load case or you change the data, if you would like to visualize certain elements or highlight certain elements, it could be done. But also the other way around, and I think this is really important, you can start from the graphs, make a selection based on the data that you are seeing, and then referring back to these structural models. And this is something that I think is quite important to mention. We often start from our digital models or structural models, and we make a selection based on what we think a good selection might be. So for instance, let's take all the beams at a certain floor or all the columns on a certain floor of a building and look what the data is, what the data looks like attached to these elements. But in this approach, we are starting from the data, we are starting from these interactive graphs and then referring back to our structural three-dimensional geometries. And I'm not saying that one is better than the other. I just think they are both very valuable, but that emphasis should be put also on starting from the data and maybe starting from graphs. And I'm saying this for about 1 year now, but well, it's just Sunday afternoon programming. But a release, a professional release of the tool should appear quite soon. If you are interested, then you can just go to the website for more information, and you can also sign up for the tool Ingbeagle when the first release would be over there. So today we are working with a whole range of tools that allow us to design digitally. Most of the time we use software by big tech companies as a kind of foundation, and then we do our own, we have our own habits to work within that framework. And some companies are really enthusiastic about everything that is going on in the community. We have a whole bunch of architects and engineers, developers that are trying out new methods, and some of these companies are really trying to implement it in their software, and that's, I think, a nice thing to also include what is going, what is happening in the community. Others are a bit more, let's say, hesitating, and their software is not changing at all. But in the end, every software tool has its, and this is not a critic on Grasshopper. I think the Rhino and Grasshopper community is a great community, and they are really developing quite fast. But every tool has its own advantages and drawbacks. And every tool and every designer is struggling with the same thing. How can we manage data? How can we get informed? How can we compare? And that is something I think that should be, when you're doing design, that's really something that you should read into and to keep, that you should read about in order to gain an understanding about the problematics that digital design actually embed. But all right, so what some solutions, you might say, well, data management and 3D models, it is all solved already. It is in BIM, where we have indeed complex 3D models, and we have a whole set of data that we can link to all these elements, that we can link to parts of the structure. We can have relations between elements, and indeed, I think, without going too deeply into BIM, because everyone is using BIM, but nobody exactly knows how to define it. But I think we have seen a whole revolution in the BIM world, where indeed BIM models are a very structured and organized way to handle data in 3D models. However, nowadays, BIM is often only used at the end of the design process, where there is need for documentation, where there is need for documenting design execution phases, where there is need for bills of materials and calculating costs and amounts of materials. But it is not at all applied as a way to design. And I think with the things that I showed today, that we can indeed, with the help of data and with the help of making interactive graphs, that we can indeed gain more insights and gain an understanding in the design process. And I think the biggest challenge for BIM is to also focus on the actual design process. And so I'm trying to do so with the tool Ingbeagle. So my last words are there. I think try to think about how you design. Everybody is designing digitally nowadays, because there are, of course, you are using paper, but rather soon you will end up designing digitally. Be conscious about how to design digitally. Be conscious about the data that is involved and that you can actually integrate in your digital models. Try to understand what's going on, and be conscious about certain design decisions, and never make decisions because you think it's a good solution, but because you know it, because you did the check based on the data embedded in these models. And perhaps you could do that based on data visualizations. Thank you a lot for this presentation.
Great, Thank you, Lennert. Fantastic. Maybe we can stop the share. Thank you so much for this insight in your world, in your profession, and what to do, but also a lot on what not to do, actually. Maybe, Laurens, you can also show yourself back. And we have some questions already from some students. One is Benoît Vrijman, and the other Arjay Kashi.
Yeah, first of all, thank you for your lecture. I think it was a very detailed and interesting lecture. I didn't know much about this whole digital visualization, but I think it's a good step forward. And my question would be maybe how accessible would InkBeagle be for designers in the future?
Well, I hope accessible quite soon. So the question is not how accessible will it be, but it's just how soon will it be accessible.
Well, maybe my question is more how easy is it to implement it in a design process?
But implementing it as a Grasshopper plugin, or it is implemented like that. So in that way, rather easily, you just install your Grasshopper plugin, which is just dragging one file in your library. So then it is installed. So in that way, it is limited to Grasshopper, but very easy to use. But maybe other, I mean, when designing digitally, you see, or I see at least a whole different, I see a whole range of different ways that are explored by digital designers. For instance, what the Block Research Group is now proposing to use the Compass framework, which can be used with Rhino, but also in Revit, Blender. It is in fact just a native Python programming environment, and they are just sharing all the algorithms that they have so far and data structures. In fact, that is also something that is quite related in the way I raised the question, how can we deal with data while designing? They prefer to do it in a very native programming way. But once you have your data structures, it can't be too hard to create graphs from it. I think what InkBeagle does differently is that you can actually make the relation between your geometries in Grasshopper, and that you can highlight certain geometries based on selections in the graphs, or vice versa.
Yeah. Okay, perfect. Thank you for your answer.
Well, my question is more like your work related. As an architectural engineer, do you go by the setting that form is defined by structure, or is the structure the response to the form?
But, well, there is no good answer for that. You can design whatever you want in a way that if you make your form follow the force or your structure, then you can read the structural behavior by the form. If you go the other way, where you start from a certain form, you are not really informed about what the structure might do maybe in the first place. But in the end, it will be a combination of both, obviously. And so obviously, when you are doing bridges or long span structures, stadium roofs, you need to have your form inspired by your forces, because otherwise you won't be able to make your spans and to make it structurally work with the amount of materials and costs that are related to the project. So you have a certain amount of money that can be spent. There is a certain cost. And so based for that, engineers and designers, when they are meeting large spans, well, they will optimize it. And so in that case, indeed, your form will be, your force will dominate what your form needs to be. On the other hand, I think with the examples I showed and with the example of the ostate shell, there are still a lot of opportunities where we should not let force, neither form dictate what something should be. We need to get informed, and it is up to the designer which impact he or she would allow. So if the impact of choosing for a certain form has tremendous impact on the structural behavior, and it is not cost efficient to make a decision based on a certain formal preference, well, then you just need to get informed, and then you will finally very quickly, I think, end up by following the forces. But for me, the question in itself is not so relevant, because in a design process, it's not so strict to just say, do we follow forms or do we follow form?
Yeah, okay. Thank you. Thank you a lot for the lecture too. It was really good to be present for it.
And maybe do a follow-up on this.
Yeah.
Lennert, when you designing a structure, to be able to design it, you have to materialize it first to know the forces. So what is first then? Is it the material or the forces? And how you deal with that? And in relation to the question that was just raised.
Yeah, and that is something in my research where I have spent, I think, too much time on trying to answer that specific question, because indeed, when you are, for instance, the example of the bowstring geometries, if we make, you can do form findings whatever you want, but there will be bending forces in your main girders, in your deck. But if you make your main girders rather stiff, then obviously the forces will be higher as well. So making something stiffer will also attract these forces. And so there is no good way, or I tried to, well, there is a good way for isostatic structures. We have obviously answers for that, and most of the optimization algorithms work that way, that you work with isostatic structures and then you immediately see what you need. But most of the structures that you do are indeed hyperstatic, and then your cross sections, your materials are dictating your behavior. And so I did a study about, can we bypass this question? Can we? You can't. That's a short answer. So what is, in my opinion, the best way to do, and I think it's done by all engineers, you just apply some reference cross sections, what I then called it. What you think, I mean, as an engineer, you have some feeling, you look around and you have a feeling about what a proper size is. You apply that. And so most of the time when you are making, for instance, for the grid shells that I showed you, obviously, because it is a hyperstatic structure, the influence of forces might differ. But for that reason, I also included the graph before and after cross-section optimization. Okay, I will not go into cross-section optimization. That's a whole other topic, and you get very unexpected results very often. But at least doing that optimization algorithm and checking before and after allows you to see the impact on the internal forces. And if you, for instance, also could link what the change in cross-section is, you are very informed about what you are actually working with. So I think the methodology that I investigated is not so much a question about does it really help to inform you about the structural behavior? Well, that's what I showed. Indeed, it might help, but I think it is applicable to a whole range of issues or questions that need to be solved within the structural design process, and even we can even go further where we can solve or where we can gain insight in geometrical issues related to structure sustainability. So wherever there is data, we are able, or we should be able to make informed decisions and to make these comparisons in a more informed way, in my opinion.
Yeah, in the meantime, I still have another more general question for Lennert also on, you talked about the non-numerical parameters, and so they are important in design, structural design, but obviously also in architectural design, things that we cannot put numbers on, but are important to evaluate in the whole process. So my question is a bit on the design as the tool that you're developing, or the world of the parametric design and the ability to put things into numbers, whether it's not a dangerous path, because there is also this domination of numbers. So when you are making decisions, like you've shown when you're looking at the structures, you're making decisions based on numbers which are easy to compare, or not so easy as you've shown, but still they're somehow you can say that a 3 is more than a 2. But how does it relate then to, for example, looking outside as a value, or not being able to see something? And based on the numbers, I might be a bit afraid that we are going to end up looking only at the numbers and forgetting about the non-numerical. So is this a bit like the splitting of the atom? It's really interesting that we are able to do it, but are we not creating also a dangerous weapon that is going to backfire at us as designers?
Well, in my in the research I did not put emphasis on architectural choices, because for me that's not so important in itself. But the main idea is to let enough space in the methodology of using data to actually also include it by having the relation with these 3D models, so that you can actually include also indeed these non-numerical things. But for me, in terms of the research, it was not important, because yeah, you can end up with a very vague discussion about what that needs to be. But that's why this the use of the data in the way that I propose, or the methodology that I show, to just get into the data, it doesn't deny the fact that there are non-numerical parameters. It is just an additional layer of information based on which you can get informed. And if you as a designer think certain non-numerical parameters are very important to take into account and to make really decisions that might go against the numbers that you have, you are I have nothing to say about what you do, but I mean, you can do whatever you want, but while looking one eye on the data, you at least know what the influence is. While that's often not always checked in design processes. And in that perspective, it is fairly different from all these optimization algorithms. And as I showed, even with these multi-objective optimizations, the designer will find himself in choosing and making these trades-offs. So no, I am not at all scared that the role of the designer will disappear. I was trying to not answer the lecture's title, but now I am. But yeah, in the end, I'm not afraid that that computers will take over. And the role of designers will be important, because we are designing for people. We are designing for the built environment, for people. So we want to have the entire design process in our hands.
Thank you.
We have a question in the Q&A that is super related to this, maybe already half answered, but Bryana, maybe you want to explore or expand a little bit on what was just discussed.
Hi, yeah, it was about using or teaching digital modeling techniques in architectural education, because in my experience, there's been sort of a resistance from the faculty to, to teach these digital modeling techniques because they feel it limits creativity from the students in terms of design, especially early on. And so I was wondering what you think about that, if it's a tool that we should be learning as students, because then when we go into the profession, we can use BIM more interactively instead of just as documentation as it is now.
And what exactly are you talking about? What kind of tools?
Like teaching like Revit or Grasshopper or softwares like this in the educational, like in a course or in a studio, because I haven't ever had a course or had the opportunity to take a course that teaches you these programs. It's sort of been figure it out for yourself because the faculty hesitates to push us in that direction, I feel like.
Yeah, so
So do you think it should be implemented into curriculum, or is it still something that limits creativity for young people?
To find the proper words. I think it is, I don't have an answer for that. I think it is always tricky as an educational department to focus too much on software itself. Because software is evolving, not in the methods, but it is evolving on where is which button. And I mean, if a course in one semester will explain you where to find each button in the software, well, that's a bad course. It should not be about the software itself. In my opinion, I think you can learn that in practice once you get in a professional field. But on the other hand, you will need these tools, obviously, to do your education. So I'm quite a defender of the figure it out yourself, but that's my personal opinion, because I don't like the focus, and students tend a lot to focus on specific softwares, how to do this in Grasshopper, how to do this in Revit, and that's not the most important question. I think it is about what students should learn, how to make up their methodologies, how to think parametrically, how to think in a digital design environment, but it should not be limited on the use of a single software, I think. But on the other hand, obviously, once you are done with your studies, you are going to the professional field, and there they require you, or they think you are fully capable of using the software. So that makes it a difficult discussion.
Thank you.
Yeah, I think it's a dilemma, because it's also very hard to think. You say you have to start thinking designing in a digital environment, and to do so you need to be super familiar with that tools, probably with the digital environment, because once you I mean, you can only start making music on the piano when you know how to play the piano. And I wonder if it's not the same here, that let's say the mastering of the tool, there it starts to open your mind to use that tool freely and creatively.
Yeah, it's funny because I used exactly the same metaphor one time in another lecture, where I showed a stage full of musical instruments, but without people. And it's the same, like referring to software as being these instruments, which can do great stuff, but not without the people. And you cannot just put anybody on the stage to get good music. These people need to get trained in order to do so, and so that it requires expertise. And when I was teaching at university, I had the impression that a lot of students, although they had some courses in programming and ICT things, that they often think of software as a one-fits-all solution. I would like to design a tremendously complex compression-only grid shell, So they put in 2,000 different elements in the structural model. Okay, I press the button, calculate, and then oh, the computer says error. Yeah, I have a question, sir. The computer says an error. So how to eat an elephant? It's one bite at a time. And also there, it's kind of prototyping. Start small, try to understand what the software is doing. But I think there is indeed not so much a need to understand how software specifically works, but rather to understand processes that you could use to design, but also understanding basic programming in order to understand why your computer is not able to solve it, and try to think abstractly. If you don't find solutions in a how is it called, in a group of equations, well, you need to know what's going on. And also that can be found quite easily by plotting the graphs of these equations. But yeah, it's a small joke.
Is there more coming, Thomas?
Yeah, if possible. Yeah, thanks. I think this is a very, very interesting discussion and conversation. And I tend to think that that as designers, the core of our profession is to identify what matters and to identify what is valued. And therefore, I would say that lectures like these are super important, because when you have to ask the questions about what matters and what you value, what is valued, it is also important to know where your questions are going to end up in what kind of system, in what kind of protocol. And therefore, Lennert, I would really like to thank you for giving us insight in your part of that of those protocols, because understanding those protocols, whether they are algorithmic, whether they are visualizations, etc., is crucial for the designer in order to know what kind of questions to ask, how what kind of data or how the data is processed. Again, in order for us to be able to ask the correct questions of what we value and what matters in a design. So, Lennert, thank you very much for giving that insight. So not really a question, just kind of an observation or reflection.
I'm very happy with what you said.
Maybe we should actually use those words to resonate and wrap up our conversation and end the night by thanking you again, basically both of you, because we wouldn't have known Lennert if Laurens wouldn't have introduced you to our faculty. And that was indeed a pleasure. I enjoyed it a lot. So thank you again, both, for being with us. Let's hopefully stay tuned, maybe do more together. And all of our audience, thank you very much for being here. Stay in touch with the program, stay in touch with our lectures, sign up for the newsletter to follow more, and hope to see you next week or soon. Have a great night, and see you later.
Bye-bye.